Hello, my dear students. Today I am going to teach the differences between real gases and ideal gases. Actually, in this class, it is a short video after learning ideal gases and real gases. The differences between two types of gases can be studied in a short time. Okay, generally this is going to be very helpful before going to examination. Not to understand entire topic. After learning ideal gases and real gases, before going to any examination, you can go through this video for quick revision. Okay, so let's see the chief differences between ideal gas and real gas. Ideal gas, in fact, there is no intermolecular forces between molecules of ideal gases. So it means neither repulsive forces nor attractive forces. No intermolecular forces. It means intermolecular forces are two types. We know repulsive forces and attractive forces. So neither repulsive forces nor attractive forces are present between molecules of ideal gas. It means, in fact, we know between molecule and molecule somewhat weakest intermolecular forces are present. Even you see non-polar and non-polar, then also dispersion forces are present. So if there is no attractive force at all, it means this gas is in fact hypothetical in nature. In reality, there is no existence of ideal gas, but still, on the basis of behavior of gas, actually same gas behaves like ideal as well as real. At different conditions of pressure, volume and temperature, same gas behaves like ideal and real gas. So on the behavior of gas, a particular gas, we can classify gas into two types, ideal and real gas. But in fact, this is hypothetical. And let's see real gases. Intermolecular forces are operative. It means actually intermolecular forces means in general students think that only attractive forces, but in fact two types of intermolecular forces are present, either attractive or repulsive. Two types of intermolecular forces are present, attractive or repulsive. So let's come to next point. Volume occupied by the gas molecule is negligible in comparison to the total volume of the container. You see, this is the container and these are gas molecules. So the volume occupied by single gas molecule is negligible in comparison to the entire volume of the container. Negligible. Okay, why sir? Because gas is free to move. Gas molecules are free to move, and free volume, the entire volume of container is the free volume. Okay, so this is the volume of the container. Volume of container in PV is equal to nRT also. This is not the volume of gas molecule. This is the volume of the container. Okay, this is pressure of the gas. Okay, because gases exert pressure inside the container because of collisions with walls of the container. We know gas molecules are free to move according to kinetic molecular theory. These gas molecules strike with walls of the container. So during so they exert pressure inside the vessel. Okay, so let's come to this. The volume occupied by gas molecule is significant in comparison to entire volume of the container. Generally, you see the difference between ideal gas and real gas. The chief difference. I have taken nitrogen gas. Suppose nitrogen gas in this big volume, big container and small container. In small container, you see the molecule, single gas molecule, volume occupied by single molecule is not negligible, that is significant, that is considerable. Okay, so let's talk about next, what are the favorable conditions for any gas to behave as ideal gas? That is low pressure, high volume and high temperature, because when pressure is low, volume is high, and high temperature, you know, low pressure and high temperature molecules start to move away from each other. So that's why in higher volume already pressure is low, and at high temperature kinetic energy is more, so molecules start to move away from each other. So generally we can say that attractive or repulsive forces are negligible. So when it comes to this high pressure, small volume, obviously high pressure means small volume, or if you take gas in small volume, obviously pressure will be high, and low temperature. Actually, you see a small volume I have taken. Okay, so gas is placed in small volume. Then in small volume, gases have restricted movement. Here gases have free movement. They can move in throughout the container. Okay, all total volume. But here not like that. Gases are restricted to move in a particular volume. Okay, so that's why when same gas is taken in small container, that I mean between molecules distance is small, so some intermolecular forces are operative. Okay, when molecule come close together, intermolecular forces are operative, either attractive or repulsive. And generally when you maintain high pressure and low temperature, in high pressure molecules come close together. Okay, they come to close vicinity, and low temperature kinetic energy decreases, so both favor increase of attractive forces. So real gas condition, these are favorable condition for real gases, and we know ideal gases obey ideal gas equation, that is PV is equal to nRT, but real gases do not obey ideal gas equation, but they obey real gas equation, that is also called van der Waals equation. Okay, P into P plus En square by V square. For n moles I am writing here nRT. This is for n moles. For 1 mole also you can write, it is equal to, this is for 1 mole of gas molecule, this is for n moles of gas molecules. So this is the chief differences. Some other differences are there. I mean, I am going to move to compressibility factor. Let's check compressibility factor. If we talk about pressure inside the vessel, okay, you have real gas and ideal gas. No doubt pressure exerted by ideal gas is more than that by real gas. That's why this is actually the pressure. You see, pressure of ideal gas is greater than pressure of real gas. Because you know, in a closed container, the pressure exerted by any gas is due to collisions with walls of the container. Suppose in ideal gas, you have already seen there is a big container, I mean volume is large, so molecules are free and they can strike, almost all molecules strike the walls of the container. But here it is not like that, because when it strikes with the walls of the container, so this one, okay, here some molecules are there, na? So the molecule attractive, some interactive forces are operative, interactions are operative. So it cannot strike with walls of the container just like ideal gas, because it between this and this some interactions are there. So this molecule drags this one, so that it cannot strike the walls of the container with greater ease as in ideal gases. So that's why pressure in ideal gas is greater than pressure in real gas. In order to equal them, pressure of ideal gas, pressure of real gas, some correction is required. Some correction, that is called pressure correction, that is Am square by V square. Okay, and when it comes to volume, we know volume of ideal gas, when you compare about gas molecule, is much lesser than real gas. Why this? We know in ideal gases the volume occupied by single gas molecule is negligible, but here the volume occupied by single gas molecule is significant, not considerable. So we can say that negligible volume, okay, gas molecule, this is not that particular entire volume of the container. I am talking about volume occupied by gas molecules. So negligible, significant, obviously this one, so real gas, it means in order to equal real gas minus some correction is required. Okay, some correction, that is NB here, this is volume correction for n moles of gas. For 1 mole you can write V minus B. A and B are van der Waals constants. You know already, there is a separate discussion about A and B after real gases and compressibility factor. You can refer your notes for details of A and B and units of A and B. Okay. Now let's go to next point, that is I think point number 5. When we talk about compressibility factor, what is compressibility factor? Compressibility factor is the measure of deviation of real gases from ideal gas behavior. Okay, compressibility factor is actually Z, that is PV upon nRT. We know in ideal gases PV is equal to nRT, so Z should be 1. For all ideal gases, compressibility factor must be 1. And what about here? For real gases, PV is not equal to nRT, so we can say that Z is not equal to 1. It means two cases are there, Z is less than 1 and Z is greater than 1. So Z is less than 1 means negative deviation from ideal gas behavior. Some real gases show negative deviation from ideal gas behavior, and some gases show positive deviation from ideal gas behavior. So when Z is not equal to 1, we can say that real gases deviate from ideal gas behavior, and the deviations are two types, negative deviation and positive deviation. Okay, so what is this negative and positive deviation? Already in NCERT we are mentioned clearly, okay, about this Z, that is compressibility factor. This is for ideal gas, Z value 1. And pressure, some gases continuously show positive deviation. Gas like nitrogen initially shows ideal behavior, later it shows positive deviation. Some gases show this particular negative followed by positive. This is negative deviation when Z value is less than 1, Z value greater than 1. Okay, so Z value greater than 1 means what? PV is greater than nRT. Here PV is less than nRT. Okay, so why this deviation takes place, sir? Simple. Negative deviation is due to attractive forces, positive deviation is due to repulsive forces, but no gas shows, no real gas shows continuous negative deviation. What is the reason for this? You see, in negative deviation, attractive forces are operative. Positive deviation, repulsive forces are operative. Operative in the sense, attractive forces dominate repulsive forces, repulsive forces dominate attractive forces. So my question is that why don't some real gases, or why don't real gases with negative deviation show continuous negative deviation? Okay, so why not continuous negative deviation? Generally we know negative deviation is due to attractive forces. Attractive forces dominate repulsive forces. Here repulsive forces dominate attractive forces. So what I am telling now, so in case of Z less than 1, it means attractive forces. When attraction takes place, when molecules come close together, when molecules come close together, attractions are operative. But when they come close together, I mean the distance is even very small, then repulsive forces start to operate. So up to moderate distances, attractive forces are operative. If we want to make them to come close together, even more close together, then repulsive forces are also operative. So that's why after negative deviation they show a positive deviation as well. So overall we can say that the negative deviation is due to attractive forces, but there is no continuous attraction. But repulsive forces are continuous, so that's why they always show positive. So any gas, some gases generally show positive deviation, some gases show negative deviation, but any gas which shows negative deviation finally shows positive deviation. Okay, so these are chief differences between ideal gas and real gases. These are very helpful before going to the examination. Okay, thank you very much.